inner sphere electron transfer rate. It is given by the equation K1 K3 upon K2 plus K3 to consumption of the oxidant into consumption of the reductant. Here, K3 is the overall mass for the sector, and it has been observed that in some cases, K is larger than K2, and if it is so, the rate determining step is simply formation of the precursor complex. Therefore, it reduces to rate is equal to K1 into concentration of oxidant into concentration of reductant. On the other hand, if K3 is smaller than K2, then it reduces to rate is equal to K into K3 into concentration of the oxidant into concentration of the reductant. So these two rates, limiting rates, I am saying limiting rates are very important for and if we have a look about the first one, we can say that it is the precursor complex that determines the rate of the reaction. Formation of the precursor complex. If you look about the second one, you can successor complex to the final product will lead to basically will determine the rate of the reaction. And someone has raised a question: how exactly one can is it possible to characterize the uh, intermediate produced exchange? Well, lies over here that there may be a case where rate is given by K into K2. K is simply equilibrium constant for this reaction. This one into K3 into concentration of oxidant and into concentration of the reductant. And if it happens so, the resulting intermediate complex will be quite stable and it will determine rate of the overall reaction. And I will take one such example while dealing with the uh, fission of the successor complex or cleavage of the successor complex. Now, as we have discussed about what are the factors that influence the rate of outer sphere electron transfer rate, we are supposed to have similar discussion about the factors that influence the rates of the inner sphere electron transfer rate. So, very first thing is formation of the precursor complex. And I have already said that precursor complex formation takes place wherein first of all the ligand, coordinated ligand from the reductant metal center is given out, vacancy is created, then the oxidant OXX group attacks the reductant metal center. Now, how we delete how far the coordinated ligand from the reductant metal center can be given out, we certainly determine the rate of the reaction and formation of the precursor complex. So I have basically you have seen and you know that a D3 metal ion is relatively inert to substitution, while high spin D4 and D5 complexes are labile. So basically, while dealing with substitution reactions about octahedral metal centers, you might have already basically gone through it and might have taught in your classes that D3 metal ion is relatively inert, while D4 and D5 complexes are labile. Another important thing is that in inner sphere electron transfer reactions, usually the vanadium 2, chromium 2, and iron 2 complexes are used as vanadium A pi star 3 sigma star 0, chromium 3 plus, chromium star 3 sigma star 1, and iron 2 plus pi star 4 sigma star 2. That's their electronic configuration. And if we have a look about the rate at which these iron lose the coordinated ligand. Four examples have been shown over here. Hexaequovanadium 2 plus, replacement by a labeled water molecule and thiocyanate. So this labeled water molecule, this reaction rate of reaction is 1 into 10 power 2 per second. On the other hand, for vanadium 2 with thiocyanate, it is 28 per mole per second. And for hexaecochromium, it is 10 power 9 with the labeled water, it is 10 power 9 per second. And for hexaecoiron, it is 10 power 6 per second. You can see that with vanadium, it is rather slower. With iron and chromium, it is rather faster. And in inner sphere electron transfer reactions, the very first step is formation of the precursor complex, where the Levine ligand from the reductant is replaced and this complex is formed. Thus, the rate at which this ligand is given out will control relative rate of the electron transfer reactions in that sphere electron transfer reactions. And in this table, it has been shown that some chloropentamine complexes, cobalt complexes, have been taken as the oxidant and as reductant. The metal the complexes based on vanadium, vanadium 2, cobalt, chromium 2, and iron 2 has been taken. And as far as bridging ligand is concerned, this is the R here. I have written R F2 plus, RCl2 plus, RBr2 plus, and so on. You can see that R is common in all these 8 examples. So this R represents CONH3. So the complex can be taken as fluoropentamine cobalt 3 plus, fluoropentamine cobalt 3 plus, bromo, iodo, azido, thiocyanate, then isothiocyanate and is oxidative complex. And you can see that from some of the examples are monoanionic. Then basically one example is for a dianionic ligand or present ligand is dianionic. Right. If you have a look about the rate of the inner sphere electron transfer that occurs between the pentamine cobalt complexes and vanadium 2 plus complex. When this is changed, the present ligand is changed from chloro, bromo, iodo, azido, thiocyanate to isothiocyanate and oxidate. Rate of the reaction changes. But basically, it is for fluoro derivative, it has not been determined. For fluoro, it is 7.6. For bromo, it is slightly higher. For iodo, it is 13. For azido, it is 13. For thiocyanate, it is 0.3 and per mole per second. And for azido, it is 12.5. On the other hand, if you see that the same reaction is carried out with hexaecochromium 2 plus instead of hexaecovanadium 2 plus. This rate of reaction is 2.5 into 10 power 5 and basically almost in the same range 2.5 into 10 power 5, 6 into 10 power 5, 1.4 into 10 power 6, then 3.4 into 10 power 6, and so on. And iron 2 plus iron 2 plus complex also this lies in almost the same range. I'm not going to read out all this, but simply I will discuss. And similarly, for pentamine ruthenium 2 plus complexes have also been rates have also been determined, particularly using hexaecochromium 2 and this data is shown over here. You can see that if we look about the electron transfer reactions in presence of vanadium 2, It is almost in the same range as that for substitution of a coordinated ligand on the vanadium 2 with a ligand like labeled water, or another example we have taken as the thiocyanate. But for the iron 2 plus complexes and chromium 2 plus complexes, it is much lower than the water displacement reaction or ligands replacement reactions in such reactions. So available data on vanadium 2 reductions shown in that table clearly shows that when this ion is employed as an inner sphere reductant, the reaction rate is controlled by rate at which water is given out from the coordination sphere of the vanadium. I have already clarified about it, and also it has been concluded on the basis of similarity of the rate of the electron transfer reaction with the rate of water substitution on vanadium 2 ion, and